my third Uruguay workshop. I'm sorry I'm not in person, but hopefully next year. So I'm going to just give you an overview of fundamentals of fluorescence and some methods. And obviously this will be expanded on in enormous detail in the applications and the rest of the talk. So the first thing we might want to ask ourselves is, why do fluorescence? Now, I always like to start off by saying it's pretty, but that's not just a funny sort of an answer. When I first joined the laboratory of Gregorio Weber, we'll hear a lot about him later, as a graduate student, he pointed out to me that he was initially attracted to the fluorescence field partly because of the aesthetics of it, the fact that you have these beautiful colors, and by looking at small changes in the color, you understood events at the molecular level. So he always reminded me to always appreciate the aesthetics of it. Now, also, fluorescence provides information on the molecular environments. There's been fluorescent probes that can sense virtually anything now, and you probably know about many of these that can sense different ions, temperature, polarity, etc. So you can design a probe to investigate or monitor almost any physical or chemical environment. But for my interest, it provides information on dynamic processes. And molecular probes are essentially, fluorescent probes are essentially molecular stopwatches. And they monitor events that happen during the excited state. So you attach this molecular stopwatch to your molecule of interest, and then when it absorbs the photon of light, the stopwatch starts, and when it emits, it stops. And that's where it's going to be very useful for much of what we see. Well, coupled with modern fluorescent microscopy, and you'll learn a lot about that, and fluorescent proteins like GFP, etc., fluorescence provides extremely detailed spatial information in living cells, as well as information on the dynamics of cellular components. It's also, as we know, very, very, very sensitive. Working with subnanomolar concentrations is routine, and even single molecule studies are possible with some effort now. So what kind of experimental systems are accessible to fluorescence? Well, we can have protein and DNA, macromolecular structure and dynamics, cell organization and functions, engineered surfaces for high throughput screening, live animals. Instrumentation includes fluorimeters and fluorometers, and we'll learn the difference. Microscopes, you'll hear mainly about microscopes, high throughput plate readers, and intravital imaging with live animals. Now, virtually all fluorescence data required for any research project will fall into one of the following categories: the fluorescence emission spectrum, the excitation spectrum, the quantum yield, the polarization or anisotropy, and the lifetime. And in this lecture and other lectures, we'll examine each of these categories in more detail and discuss the concepts and practical considerations. But to understand fluorescence, it helps to look at what's called the Perrin-Jablonski diagram, which is sort of the history of excited state electron. So you have molecules that at room temperature are normally in the ground state here, and there's different vibrational levels in this electronic ground state. And then they absorb a photon of light, and very, very fast process, takes less than 10 to the minus 15 seconds, and go to an upper electronic state. You can have the lower upper electronic state or higher ones, but regardless of where you excite, you have rapid internal conversion, vibrational modes kick in, and you come down to the lowest vibrational level of the first excited state. And that's where things can happen. You can sit there, and while the molecule is there, you might have some process like intersystem crossing to triplets, phosphorescence. We will not talk about that. You might have radiationless decay where it just falls back to the ground state. But the interesting thing for us, of course, is when you get fluorescence emission, okay? And this can take place on the order of nanoseconds after excitation, as we'll learn more detail later. So in a typical emission spectrum, the excitation wavelength is fixed and the fluorescence intensity versus the wavelength is obtained. Here we see several different spectra for quinine sulfate, fluorescein, rhodamine, ethidium bromide. And here's the cuvettes holding those compounds so you can see with your eye the colors that correspond to different wavelength of emission, okay? And let me just say that when you work for many, many years in the field, your eye is pretty good. And just by looking at the color, you have a pretty accurate estimation of where the emission maximum is, which is useful. Now, examination of a large number of emission spectra over many years resulted in certain general rules. For example, in a pure substance in solution in unique form, the fluorescence spectrum is invariant. It's the same independent of the exciting wavelength, and that's an important fact practically for many things we do. Also, the fluorescence spectrum lies at longer wavelengths than the absorption. Also, the fluorescence spectrum, to a good approximation, is a mirror image of the absorption band of least frequency. Now, let's look at that in a little more detail. So here's fluorescein in a cuvette, the emission spectrum, and this is a solution that's being excited at 470, this blue line, and also at 375, this red line, and at 280, this black line. And all I did to take this data was change the wavelength of excitation. But you can see that you get much more emission when you excite at 470 than the other ones. And this is simply because the molecule absorbs more at that wavelength, and that it instrumental parameters, there's more or less light at different wavelength. But if we normalize these all to the same height, you see it's exactly the same. And that's the important point. It's invariant. So in fact, if you have a solution and you look at the emission with different excitations and it changes, it usually means you have an impurity in the solution. And I've had people who thought they knew a lot of fluorescence that overlooked this one little fact. So it's always a useful way to tell if you have a pure thing in solution. And note here, I'm not correcting, there's instrumental things to correct, but we're not going to worry about those factors. Now here, the spectrum fluorescence lies at longer wavelength than the absorption. Here you see the absorption spectrum of fluorescein in black, and you see the emission in green. And generally it's shifted to the right. There is some overlap, but no matter where you excite the fluorescence in that black absorption envelope, you'll get that emission shifted over, okay, to lower energy, higher wavelength. And less important is this observation, but to a good approximation, the fluorescence is the mirror image of the absorption band of the last absorption band. And here you see rhodamine and ethanol, and you can see absorption and emission. And that's not so important, but it's interesting because all of these observations follow if we consider the Perrin-Jablonski diagram. So we can excite at different levels, but as we said, no matter where we excite in the excitation energy manifold, we get rapid dipolar de-excitation till we come to the ground state. So hence, it doesn't matter what wavelength we excite with, we always start the emission from the same place, namely the lowest vibrational level of the first excited state. Okay. And at room temperature, the fluorophores usually are in the lowest level, as we see here, and we excite up the different levels, but the emission always starts at the lowest level of the excitation and goes to different levels in the absorption, as you see here. This means that the fluorescence is going to be generally of lower energy than the absorption. So that accounts for that shift, which is called the Stokes shift. We'll see why in another lecture. And the fact that the spacings of the energy levels in the vibrational manifolds of the ground state and first excited state are similar accounts for the mirror image law. So let's talk first about the excitation spectrum. So here we're looking at the relative efficiencies of different wavelengths of incident light to excite the fluorophores. Okay, so you keep the emission wavelength fixed and you change the excitation. Now, if the system is well behaved, these general rules would hold, and the excitation spectrum will match the absorption spectrum. Although you do have to do corrections. So here's an example. This is an overlay of the absorption spectrum and the excitation spectrum for ANS and ethanol. And we see they're a very, very good match. Note I say corrected because actually there's a lot of corrections to correct the excitation spectrum for different outputs of the light source with wavelength, et cetera, et cetera. But we're not going into those details in this course. Now, of course, if the excitation absorption spectrum don't match, then it gets interesting. For example, here's the excitation spectrum for a fluorophore free in solution. Okay, first we'll look free, and that's the excitation. The emission spectrum, of course, would be out here to the higher wavelength. But in this case, suppose we look at the same excitation spectrum for this dye bound to a protein, we might see something like this. And that's because the protein, the tryptophanes, for example, and the tyrosine, we'll learn more later, can absorb light in the UV at 280, for example. And if it's situated where it can transfer the energy to the fluorophore, you would then excite the fluorescence of the fluorophore even when you're going at 280 nanometers. So this is why we often look at excitation spectrum to see if we get information about these type of processes. Now, the quantum iode. The quantum iode is a concept introduced in 1924 by Vavilov, and the simplest definition is it represents the number of photons emitted divided by the number of photons absorbed. And you have to do that, not energy emitted over energy absorbed, because obviously the emitted photons have less energy than the absorbed. Okay. So if a fluorophore absorbs 100 photons and emits 100 photons, the quantum iode is 1 or 100%. If it absorbs 100 photon, emits only 20, then the quantum iode is 20%. Okay, but a more insightful definition would be quantum iode is the rate of the emission process divided by the sum of the rates of all deactivation processes. So you have Kf, for example, would be the rate of fluorescence, and Kd would be the sum of all the rates for processes which depopulate the excited state. Non-radiated deactivation processes may include photochemical and other events, but we're not going to go into these different processes. But here's a list of quantum iodes from Bernard Valleur's wonderful book, Molecular Fluorescence. And I'm bringing this up for a purpose. You can see different things like benzene is a very low quantum iode, tryptophane's a little higher, 0.14. Once we get up to rhodamine, we're up at 100%, a quantum iode of 1. So essentially, though, the quantum iode is what determines if a fluorophore is useful. There are many molecules that emit fluorescence, but it's at such a low level that we don't even think of them as being fluorophores. For example, the nucleic acid bases, adenine, guanine, etc. These have fluorescence, but the quantum iode is unbelievably low, like 0.0001 or something. So in fact, it's not useful as a fluorophore. So sometimes the very definition of what is a fluorophore will depend on what the quantum iode is. Okay, and it's hard to work on molecules that have a very low quantum iode, although it still can be done with some effort. But I also want to bring up the point that quantum iodes are very difficult to measure. Okay, if you look at literature values, for example, for quinine sulfate, which is one of the standards, you see literature values going from about 0.5 to 0.7, and that's done by good groups. So that's why when I review a paper where they talk about a quantum iode, I like to see what they used as their standard, what value they used, and how they did it. And it's important to know these things to really judge the value of a quantum iode. Now we're going to talk a bit for a while now on polarization. And although you're not going to hear a lot of polarization during this workshop, I think polarization or anisotropy, we'll see the difference, is a very important fluorescence parameter that's widely used. So you should really have an awareness of this. So We know light can be considered as oscillations of electromagnetic field, characterized by electric and magnetic components which oscillate perpendicular to the direction of light propagation, as shown here. But we're only going to be concerned with the electric component in these lectures. So in natural light, the electric field component can assume any direction perpendicular or normal to the light propagation direction, as I'm trying to illustrate here. But polarizers are optically active devices that isolate one direction of the electric vector. So here I insert a polarizer and I'm trying to illustrate I've picked out one of those. If I rotate the polarizers, I'll get a different one. And we'll talk more about polarizers in another lectures, but this is a typical crystal polarizer that will pass one plane of polarization. So let's consider this coordinate framework with the fluorescent solution at the origin, and X and Z are in the plane of the page, and Y is coming out towards you as the observer. Well, in this system, the exciting light is traveling along the X direction, and a polarizer is inserted in the beam, and then we can select the direction of oscillation of the exciting light with the polarizer to impinge on the sample. Okay, now the molecules in the cuvette, in this case, absorb light and give rise to emission. And to measure the polarization, we look then along the direction 90 degrees to the excitation, and we have a polarizer we can rotate, and we can look at the intensity parallel and the intensity perpendicular of the emission. And then polarization is defined as the intensity parallel minus the perpendicular over the sum of those intensities. So in theory, then, if it's completely polarized in the parallel election, you would say that polarization could be 1, which, let me tell you, can happen in a crystal, but will never happen in solution. We're going to discuss that because that's extremely important for all measurements you may do. If it's totally polarized in the perpendicular direction, you can get -1. And yes, polarization, you can actually measure negative polarizations, and we'll see how that can happen. So the limits of polarization theoretically, mathematically, are +1 to -1. Another term frequently used is anisotropy. Some of you may be familiar with that, usually designated by A or R. And that's defined as parallel minus perpendicular over parallel plus 2 perpendicular. Okay, so the limits to anisotropy would be +1 to -1/2. But these limits are not reached in solutions. But let me make a comment about the difference between polarization and anisotropy, because people get attached to one form or the other. You can easily show, given those definitions, that anisotropy is 2/3 times 1 over p minus 1/3, the reciprocal of that. Or more simply, anisotropy is equal to 2p over 3 minus p. For example, if I have a polarization of 0.5, the anisotropy is 0.4. 0.25, anisotropy 0.2, etc. And when you do measurements in a cuvette in most instruments, modern instruments, they give you the polarization and the anisotropy. So clearly, the information content of these two functions are identical, but people use one or the other due to practical considerations we'll discuss later. So if you excite an ensemble of randomly oriented fluorophores with plain polarized light, what you're doing really is a photo selection, because the probability of a molecule to absorb the light is going to be related to the angle of the molecule relative to the exciting light. And let's look more closely. So we have a fluorophore. In this case, it's a one of the Dan probes. You'll learn a lot about these later on. This is, Prodan. Now, when it absorbs light, the electron cloud moves around, and we can stabilize dipoles on the negative on the carbonyl and positive on the amine. So you can see we can have an excited state dipole moment relative to the framework of the molecule. Okay, and this is the transition dipole or the transition moment. Well, then in solution, when I'm talking about those molecules in solution relative to the exciting light, it's how this dipole is oriented relative to the exciting light. Because as we said, it's the angle is important for the probability of absorption. Specifically, the probability of absorption is proportional to the cosine squared of the angle between the excitation and transition dipole. And this is how that function goes. We can see that it falls off rapidly when we go to larger angles. If we start at 0 collinear, but even at 45 degrees, we can see we have a 50% probability. So molecules that aren't oriented totally parallel are still going to absorb the light. And we'll try to show that with a little illustration. And we excite with parallel light, and we can see molecules with the dipole, those are the lines through the circles, lined up are brighter. The ones at a slight angle are dimmer. They're not as probable to absorb. And the ones at a large angle, we don't see them at all. So that's the idea of photo selection. Okay. Now, let's consider first that the transition dipole from the emission is parallel to the absorption dipole. So I'm showing it here where blue is the absorption dipole, and then the emission dipole, when the dipole collapses and light is emitted, that has a directionality also. And let's think first, it's parallel to that. And also we assume this molecule can't rotate during the excited state. We've frozen it somehow. Well, then, if we were to measure this, we won't get 0.1 for the emission because some of the dipoles are not exactly parallel to the direction of the exciting light, as we said. Specifically, the number of dipoles making an angle theta with the vertical axis is proportional to the sine of theta. And as we go to higher and higher angles, we get more and more molecules. Well, if you integrate over both these factors, the number of molecules at different angles and the probability of cosine squared for the absorption, you end up seeing that the limiting polarization for randomly oriented molecules in solution, not rotating, it's going to be plus 1/2 or 0.5. Okay. Now, this assumes that the emission and excitation dipoles are parallel, which doesn't have to be the case. And let's look a little more deeply. So here's an absorption spectrum of actually phenol. And we see absorption of S0, S2, higher energy, and S0, S1. And we see the little Jablonski type Perrin-Jablonski diagram showing this, and the emissions at the higher wavelength. But actually, these absorption bands correspond to different transition moments that are oriented differently on the framework of the molecule, okay? And we can see that if we excite into the S0, S2, that's at a large angle relative to the emission bands, which is going to be oriented to the S0, S1, okay? And so let's see what happens. So let's consider a molecule like this, and let's suppose we excite with the S0, S1, and we select out of the population these molecules. And these are the ones that emit. And the emission dipole is parallel. So the polarization we're going to see is going to be relatively high. Now consider we excite with a different wavelength of light, and we're photo selecting a different population. I'll prove it. There's the old population, okay? This is a different one. And again, the emission dipole is now in this direction. So the polarization will be at a large angle. And in fact, you go through all the calculations we did before to get plus 1/2. If it's oriented at 90 degrees, the emission and absorption dipole, you can have a polarization of minus 1/3. Okay, and in general, this intrinsic or limiting polarization we call P0 will depend on the angle with this equation between the absorption and emission dipoles. Okay, and so the important thing, and this is the point of this whole discussion, is the limiting polarization will depend on the wavelength of excitation. Okay, let's look back at the phenol. Here, if we look at exciting it out at the edge of the S0, S1, we'd be relatively high, about 0.35 in this case. If it's not at 0.5, it just means the emission and absorption dipoles aren't exactly aligned. But then we go to lower wavelength of excitation, we drop and drop and drop the polarization, okay, because we get a bigger angle. Let's look at other molecules like tryptophan. Some of you may be interested in tryptophan fluorescence. Here we see the absorption spectrum in the dotted line or the dashed line, and the solid line shows the polarization spectrum. And many people, for example, like to excite at 295 to avoid tyrosine excitation. But here we can see it's a pretty bad wavelength for polarization. For polarization, you'd like a higher value, you should be up here. Okay. Here's rhodamine in a lucite block, and we see with rhodamine, we go up very close to 0.5, the theoretical limit in solutions, and then we can change a lot when we change the wavelength. And here's an extreme case, protoporphyrin 9 and glycerol at -20, and we see we go all over the place. Why is this so important? Let me just say it was maybe less important when I was a graduate student, because we would use lamps and monochrometers and pick any exciting wavelength we want. But now it's much more common for young people like you to use lasers. And let's say, suppose you have a laser whose wavelength is down here. Well, you're not going to get a very high polarization. And obviously it will change. You need to know the limiting polarization at your exciting wavelength, your laser wavelength, okay? And here, fortunately, we have a laser that emits at about 528, and so we can use that wavelength. But that's just to say, to guard against, because I've seen again and again at meetings, people making mistakes in their interpretation because they're not realizing the wavelength, the polarization changes with wavelength. So, okay, and here for GFP, it also happens for GFP. You get the high polarization at the long wavelength, you drop down, it changes. But this will usually never bother you in microscopy, but it could. Here we see 3 different rhodamines, and even though they're all basically rhodamines, they change a lot, the polarization. Now, in many cases nowadays, you might be doing multi-photon excitation. You hear a lot about 2-photon excitation in the course. And 2-photon excitations, you're doing a selection upon a selection, and the limiting polarization is higher, which can be useful. We see 1 photon, the anisotropy limitation would be 2/5, and 2-photon, it's 4/7, and 3 photons, it's 2/3. So multi-photon excitation actually helps you to get a bigger range for polarizations. Okay, now consider when the fluorophore rotates during the exciting state lifetime. So we have an absorption dipole, an emission, but now it's allowed to rotate during the excited state. We go through another angle, basically. So you get additional depolarization when you rotate. And in fact, you get this equation. The observed polarization is going to be related to this equation, which has the limiting polarization, which sort of sets the range you can do, over 2/3 cosine squared theta omega -1, where omega is the angle you went through during the rotation. So again, to summarize, we have a population randomly oriented in solution. We excite with polarized light, photo select out one population, then during the excited state lifetime, these selected molecules can rotate. Obviously, the other ones can rotate too, but it's the fluorescent ones we're interested in. Now, it was Francis Perrin in 1926 who related the observed polarization to the rotational diffusion and the excited state lifetime. Specifically, he got this equation where you have the observed polarization, P is going to be proportional to the limiting polarization, which obviously he understood, 1 plus RT, gas constant, temperature, mu, the viscosity, molar volume, and lifetime. So obviously, the longer the lifetime, the lower the polarization, you see, because it has longer to rotate. You see polarizations on the bottom, lifetimes on the top. But the higher the viscosity, the higher the polarization. We'll see that comes up with membranes, and the bigger the molar volume, then the larger the polarization. So we can rewrite this equation like this, where we have tau and rho is the rotation, the birotation relaxation time, the time it takes to rotate an orientation through an angle of the arc cosine of 1/e, about 68 degrees. And for a spherical molecule, rotational relaxation time is 3 μv over RT. For a spherical protein, you have this equation where you have to have the molecular weight and the partial specific volume and the hydration. So immediately you see that obviously polarization is very good for looking at rotating macromolecules, and that's important in biological studies. And again, if we have a fluorophore free in solution, it can rotate rapidly, low polarization. If it's bound to a protein, for example, rotates more slowly, high polarization. Now I'm going to make a side comment about rotational relaxation time versus rotational correlation time, because it's not uncommon in the literature to see people using rotational correlation time, which is designated as tau sub c usually, instead of the birotational relaxation time. The information content is the same, because it turns out the rotational relaxation time is exactly 3 times the rotational correlation time, but people get attached to one term or the other. Originally, when polarization was being developed, the theories with Perrin, they studied the relaxation time defined already by Debye, who studied dielectric phenomena. It was only in the 1950s when Bloch was proposing NMR measurements that he got the term correlation time, okay? So the important thing is just to know there's a difference, because when you're reading the literature, you can see one or the other. Here's the Perrin equation in terms of anisotropy and correlation time. So it looks simpler, fine. But when you read the literature, you have to be aware. And let me just say right now that polarization, you usually see people doing clinical chemistry always relating or reporting a form of polarization, whereas many biophysicists like to report anisotropy. But the information content's the same, but just be aware of what you're reading. Now, in the case of fluorescent probes associated non-covalently to a protein like porphyrins, FAD, NADH, ANS, we'll talk about more, to associate with any appreciable binding energy, the probe has to be held by several points of attachment. This means there's no local mobility. Basically, any rotation you see corresponds to the global rotation of the protein. Now, if it's attached covalently via linkage with an amine or sulfur hydrogroups, or even tryptophan or tyrosine would be a local fluorophore, you get local mobility. Things can rotate around the point of attachment. So I'm trying to illustrate that here. Here's rotation. Let's look at the rotation modalities of this dimeric protein. You have the overall dimer rotation. You have movement of one domain, the C domain, relative to the other domains, and you have rotation of the di around the point of attachment. So all of these will contribute to the observed polarization. Usually we're not trying to use polarization, though, to say what exactly is the mobility, what's going on at the molecular level. Rather, we're looking at it to see changes of states, to see, for example, aggregation state. It's ideally suited like protein dimer monomer. Here we have a fluorophore that we dilute it and it can dissociate to monomers. So you may label it with an intrinsic, maybe you have intrinsic protein fluorescence, tryptophan, or you can introduce a label. We'll talk about those in a bit. And then, of course, the monomer would rotate more quickly than the dimer, so you would have a lower polarization. So let's look at this type of plot, and these are very common plots in the literature. We look at the steady state polarization or anisotropy as a function of concentration of the protein. This top one shows fluorescein labeled lysozyme, which is a monomer, doesn't change over a very wide concentration range. But this other protein is a dimer, and the polarization does change at high concentrations. It's a plateau. We dilute it, it eventually goes to another plateau. And what we're seeing here is a dimer monomer transition. And it's important to note too, dimer monomer transitions take place over several orders of magnitude. To go from 90% dimer to 10% dimer, okay, you would actually go over 729-fold or 2.86 log units. Now, the exact value, why is that dimer polarization about 0.15? We're not concerned at the moment. It has to do with local mobility of the probes and if there's energy transfer from one probe to the other, but we don't care. We use it to follow the association. Also, for ligand binding, it's a wonderful method, okay? Because here we see a fluorescent GTP analog binding to dynamin, a GTP binding protein. And if you have 1 micromolar, this matte fluorescent GTP, and we increase the dynamin, we can see we titrate up and we get a beautiful binding isotherm. And we can get a KD from this. Now, for this sort of a thing, we have to take into account if the probe changes the quantum mute when it binds, which it does in this case, but we can extract binding constants. And this is a very wonderful method that people use. In fact, this method now is used much more commonly, as I'll mention in the history talk, than radioactivity, which used to be very popular, but now you can do so much with just polarization. And that's why it's also used for plate readers. And they use this for high throughput screening, for drug inhibitors, et cetera, where you can just, with 96 well plates or even bigger plates, do rapid polarization screening. And you can also do polarization through microscopes. I don't know if anybody will talk about that in the course, but you can put polarizers in and you can measure polarization. It's important to realize, though, if you're looking at rotation of big molecules like a GFP, it's not going to move much during the short lifetime. But this is where this phenomenon of energy transfer can be important, because you can have 2 GFPs, and if they're near each other, they can transfer energy, and that will give rise to a change in polarization. Okay, but more about that later. Well, just quickly, what is FRET? I guess I should mention that. Förster resonance energy transfer. We know we have a molecule, we'll call it a donor, but if nothing else is around, it absorbs light and emits light. But if you have another molecule with the right properties nearby, the acceptor, energy from the donor can transfer to the acceptor, which then gives rise to the emission, okay? And when you have this energy transfer, it decreases the intensity of the donor and decreases the lifetime of the donor. And that's what's going to be important for many of the lectures you're going to see in the course. So it's a great way to measure efficiency of energy transfer by looking at how the lifetime of the donor is affected. And of course, the acceptor would have more emission. So why do lifetimes? And again, what I'm hinting at, it's characteristic of a fluorophore. It's independent of the concentration, and you'll see more about that when you see people discussing FLIM data. So you can't tell how much of a probe is in a region of a cell just from the intensity. Maybe there's more probes or less, or you can't tell the intensity of a probe, let's say necessarily the quantum yield, but the lifetime will tell you an important property about in that part of the cell, what's happening. And then that's why we'll talk a lot in the course about fluorescence lifetime imaging, where you're doing an image based on the lifetime. Now, let me talk in the remaining 10, 15 minutes about fluorescent probes, because obviously none of this will work unless we have fluorescent molecules. We can talk about in vitro or in silico probes, and in vivo, more accurately in cells. Probes can be classified as intrinsic fluorophores, that is, that fluorophores that naturally part of the system being studied, or extrinsic fluorophores that are introduced. Here's an example of some intrinsic ones. NADH and FAD, you'll hear about in the course a lot. Porphyrins, you'll hear some. There's other fluorescent molecules that can give rise to autofluorescence in the cell, for example. Also in proteins, it's very important you have some amino acids are fluorescent: tryptophan, tyrosine, phenylalanine. And here on the left, we see the absorption of the tryptophan, tyrosine, phenylalanine. Tryptophan is a much stronger absorption. That's why most people work with that. And here we see on the right the normalized emission spectrum of tryptophan, tyrosine and phenylalanine. So we can also separate to some extent based on the emission properties. Going back. Extrinsic fluorophores are synthetic dyes or modified biochemicals that you can add to it. And there's usually two categories here too. Non-covalent, where it's put in and it goes to a specific region or binds to something specifically, and covalent, where we specifically attach it to a molecule of interest. Here's some non-covalent ones, like famous A&S molecules, and we'll learn more about those later, that are weakly fluorescent in water, but very strongly fluorescent in a hydrophobic environment, like hydrophobic patches on proteins or with membranes. Now, a very, very important class of probes was introduced in 1999 by Molecular Probes, the Coughlin's company, who introduced this Alexa series of probes, because he realized this is when microscopy started to become important, fluorescent microscopy, and fluorescein was so easily photobleached. So he wanted a very photostable probe. So he made a series of probes based on different dyes, like coumarin probes and fluorescein probes, or Alexa 488 is based on fluorescein. And all of these are very photostable and have very good fluorescent yields. They're called Alexa, by the way, because Haugland's son was Alex, and he named him Alexa after his son. So all Alexa dyes are more fluorescent, more photostable than their spectral analogs they're based on. And they have very wide range of absorption and emission. And this shows the photo bleaching profile. I think that was in the original paper for fluorescein, which bleaches, especially under a microscope, it'll bleach very rapidly, but the Alexa is much more photostable. Now you have a series of photostable probes, the 8O dyes and the day dyes. There's just a lot of them, but Alexa is probably the most common. And here you see the series goes over a wide range. And these are also made with chemistry, so they will react with amines or with sulfhydros, okay? So you can label proteins, and you can label a protein and you put a group on that maybe depends on what you want to look at. I always say you should, the lifetime may be an important consideration, and you can attach it to amine groups or cysteine groups depending on the chemistry involved. And there's also, of course, analogs, fatty acid analogs, phospholipids that target to membranes. And then nonpolar probes, such as this series, the Dan series. And you're going to hear a lot about Lordan and other Dan probes in this workshop. And this was made by Gregory Weber. We'll talk about him later. But the important property, as you'll learn, is that the spectral emission of these probes, like Lordan or Prodan, it depend on the environment. We see in cyclohexane, it's very blue, and in water, it's way over to the red. So you can use these to get information on the environment. And especially you'll hear a lot about Lordan work, okay? And Lordan inserts into a membrane. It's got this alkyl tail. And as the fluidity of the membrane changes, you can get more or less penetration of water, which will change the emission spectrum. Here we see going from the gel phase and the more solid to the liquid crystalline phase. And you'll see this is going to be extremely popular in this course for a lot of applications. There's also probes for calcium determinations, were very popular for years in cuvettes, and now there's new ones for microscopes for UV or visible excitation, some ratiometric, some non-ratiometric. What do we mean ratiometric? Ratiometric means, for example, here we look at one emission wavelength, but the excitation spectrum changes when you bind calcium. So you look at two different excitation wavelengths, and the ratio tells you how much calcium. Indo was a very popular ratiometric one, where the emission changes and one excitation, but you change the emission. Then you get non-ratiometric ones like calcium green. And here the intensity changes with calcium, but more importantly for us and what's used in the cell, the lifetime changes. So by looking at the lifetime of calcium green in cells, for example, you can get the calcium levels. Now, of course, there's more recently a lot of very great and popular probes. I won't go into them. You'll hear about, I think, the Janelia fluorides. You can see in the bottom right here, it's a little different squaring chemistries, but these have become very popular. They're very, very photostable, and you often see people conjugating antibodies with these and then throwing the antibodies into in vivo systems. And also now to get into some protein systems, there's things like halo tags and snap tags. And I've used halo tags personally. And the halo tags, you have a plasmid that codes for this halogenase, which you molecularly genetically, you attach that to your plasmid of the protein of your target protein. Now, when this is expressed, you can introduce a fluorophore, which has this alkane and a chlorine, and you can attach any fluorophore you want, and you can label your protein then with this. How's this useful in the cell? Well, I personally used it on a protein that was transmembrane, and we put this dehalogenase plasmid on the external part. Now we can attach, just adding to the solution above the cells, any fluorescent probe we want. And the usefulness of this is you pick any color you want, which any lifetime you want. So that's a useful technique, okay, especially I think for these membrane proteins. There's also snap tags, which is another protein that allows you to attach covalently a targeted label. Okay, and I should say the halo tag's about 33,000 kilodaltons, the snap tag's about 19. And it's both a little less than the normal fluorescent proteins, which were discrete fluorescent protein discovered by Shimomura. But I'm not going to talk about that this time because fortunately we have Richard Day giving a lecture tomorrow, and he's one of the world's experts on all fluorescent proteins. So you'll get a much better discussion from him on that. And I think, yes, that's my final thing. And I finished not only on time, but I think a little ahead of time. So I hope Leona will praise me for that.